thank you for your introduction. So,
the radar perception database using the ADSB data from the OpenSky Network. I work at Milan in the magnetism and the radar department, so it's a bit more defense-oriented than what we use from Milan. So first, how the radar works, for those who don't know, we send a signal to the plane, the signals come back, and the intensity of those signals that came
Sorry, can you move that up a bit? Because they can't hear.
Sorry.
Yeah, maybe in your...
Is it better? Yeah.
Okay.
So the intensity that comes back depends on the target, so the aircraft.
usually the bigger the aircraft, the higher the signal will come back, all things equal otherwise. This measure of how much energy is transmitted back is called radar cross-section, or RCS. So then, what is ADSB data? I don't think I need a lot of time to explain that to you. Aircraft communicate between them with ground receivers as well. ADSB data in the frames contain useful information, for instance, position, being time, latitude, longitude, altitude, some other information, and most importantly, an identifier for the aircraft, so the ICAO24 identifier. And OpenSky, the OpenSky networks, we all know, centralizes these ADSB messages and provides the public with a live API, which is very useful for us, an ADSB messages database, an historical database, a mod-S messages database, and an aircraft information database, which we all use in this article. So, and how does the automatic measurement and labeling we'll be talking about works? We receive the a receiver receives the aircraft info from the ADSB frames. It sends it to the OpenSky Live API. The Live API gives an operator, so a human or a computer, what we call sky truth, so the sky awareness around the radar. Then the operator selects an aircraft, sends this information to the radar then gets the aircraft position and can aim at the aircraft, and then the radar data recorded as long as the aircraft information are sent in our database. So, quick demonstration of how our control software works. So this is the, whoops, does this work? Yes, this is the camera of our radar, a map with the aircraft. All the aircraft have a score. You'll see the radar switching target automatically. We see that thanks to the OpenSky aircraft database, we have the information on the aircraft, the model, and the engine number, which is quite useful when you're dealing with radar data. So it works quite well, as you can see. The tracking of the turret could be improved, obviously. Another example, we are following a Boeing 777, and then the radar switches target on an A330, which is here. Oh, yeah, there you go. So you can see that we have access to a lot of different aircraft aspects, which is quite nice for radar measurements. So what are the outline of this presentation? So first, I'll dwell a little bit more on automatic radar measurements. Then how we use ADSB data to supplement the radar processing. Finally, I will talk briefly about aircraft aspect computation, and then conclude this presentation. So how do we go about making automatic radar measurements? So we use a radar called HYCAM. It's a testbed radar, not the usual radar you'll see in an airport. It has 6 independent transmit channels, 16 independent receive channels. It's for what we call MIMO radar, not very important for this presentation. It has a bandwidth of 500 megahertz, which is quite a lot. Usually civilian radar have ATC radar have 2 megahertz bandwidth. It has a peak power of 700 watts. This is not a lot, but it's a signature measurement radar. We don't need that much power. It's operating in S-band, usual band for aircraft surveillance, so around 3 gigahertz. It's mounted on a turret that can rotate 360 degrees around, elevate up to 50 degrees, and it's fully parametric, which can be useful for scientific applications. It has many capabilities, so it has been used in my PhD thesis on the detection of UAVs. So the track you see here is a UAV. You see that there are a lot of things happening in low altitude that we can measure with this radar. With a larger bandwidth, using the 500 megahertz capabilities, we can even do imaging radar. So this is a radar image of a Beluga XL from Boeing. So where is this radar? It's in Ile-de-France, in Palaiseau, near Paris. So it's close to Charles de Gaulle Airport and Orly Airport. Charles de Gaulle Airport is north of Paris, and Orly Airport is just right here, 10 kilometers away. And as you can see, there are a lot of takeoff trajectories or landing trajectories. This is 3 hours of measurement, all the trajectories we have of the aircraft we have measured. So as you can guess, we have access to a wide variety of aircraft aspects, and we have a lot of different aircrafts passing by our radar, which is quite nice for the measurements. So how do we select for the target? Each target is identified by its ICAO 24 number. We give it a score. The target with the best score is selected for the measurement. We have an hysteresis to avoid jittery switches when scores are quite close. So we need to have a good, the score doesn't just need to be good, better than the previous one. It needs to be way better than the previous one. When it's way better, we switch target. The score system we have chosen has many benefits. It's quite generic, so we can use a lot of different data for that. We use distance because obviously if the aircraft is closer, we will have more signal with our radar. So we want to have good signal to noise ratio. And angles, because obviously if the radar is out of the capabilities of our turret, if we cannot aim at the aircraft, it's not good. Then how do we use ADS-B data to supplement the radar processing? So roughly how a radar works, a pulse radar works. We send the pulse and we get the energy back from the aircraft. So here we have 2 pulses of the radar, 2 consecutive pulses measured by the radar himself. And here we have the same aircraft measured 2 times by the aircraft. A problem with radar, with pulse radar, is that those 2 peaks are the energy coming back from 1 pulse of the radar, but this peak could be the energy coming back from this pulse or this pulse. That's what we call the distance ambiguity. And that's a bit of a problem when you do radar processing. We need additional radar processing to lift this ambiguity. With radar, you know that radar are quite good at measuring speeds as well. So you can do what we call Doppler processing to measure the speed of the aircraft. So here is the aircraft. You see that there is a lot of empty space, a lot of useless data, and for the processing, we would like to only process the useful data, the data with the aircraft. So that's where OpenSky data, ADS-B data comes in. We know the aircraft position and speed thanks to the ADS-B data. We can aim directly at the aircraft, ignore all this useless information, and just extract the data thanks to that. And we can also lift the ambiguity, because this aircraft is actually not at 5 kilometers and going at minus 105 meters per second relative to the radar. It's actually going at minus 135 meters per second relative to the radar, and it's actually at 35 kilometers. So you see that with ADS-B data, this tedious process is made a lot easier. Then what we can do is compute the actual radar cross-section. So for that, we need the radar data. We need to know the distance of the aircraft. Then we have the ICAO-24. We can use the OpenSky aircraft database to learn a thing or two on the aircraft. And if you want to play, you can also look at a nice photograph of the aircraft thanks to the PlaneSpotter API. Then what we can do is compare the radar data and the ADS-B data. You might know that radar stands for radio detection and ranging. So let's talk about the ranging. With the ADS-B data, we can measure the distance between the radar and the aircraft. And with the radar, we can measure the distance to the aircraft. So I've plotted here the difference between the ADS-B distance and the radar distance and the range cell limit. The range cell of the radar is given by the bandwidth of the radar. Here we have a range cell of 75 meters. You can see that ADS-B data and radar data are in good accordance. They are very close, which means that the ADS-B data are quite accurate. For our use case, we could even, I think, just blindly trust the ADS-B distance we get, since it's always in the same range cell as the one we have measured. For speed data, it's a different story. We see that there are some jumps. Actually, those jumps can be explained with the ADS-B data. You see that there is a quantification step in ADS-B data. So this is those data are the vertical rates, and those data are the ground speed. You see that the quantification correlates with the jumps in speed error. So if this quantification wasn't there, we have all the reason to think that ADS-B data and radar data would be very close to each other. Then, how do we go about and compute the aircraft aspect? So, as you might guess, the aircraft aspect is quite important when we talk about RCS measurement. Here, I have a small model of an aircraft. You see that for different aspects, we have different visual cross-section. Visual cross-section and radar cross-section work in similar way. If you have a greater cross-section, most probably the radar cross-section will be greater. So different aspect leads to different signatures. So we want to know the aspect of the aircraft. Thankfully, we can do that with OpenSky data. So we need two referentials, one referential for the radar, one referential for the aircraft. For the radar, the referential we use is based on the antenna position. So one vector is the aiming line of the radar, one is the tilt rotation axis, and the final one is the horizontal axis in the antenna plane, and also makes a direct referential. For the aircraft, we just describe it with the classical aircraft angles, the heading, the pitch, and the roll. Oops. And the roll. So how do we compute the aspect and link it to the aircraft aspect? So with the ADS-B data, we don't have the heading, unfortunately, but we have the track, which is as good, not as good, but can be good enough. We don't have any roll data, so we use 0. And we don't have any pitch data, so we use the slope between the vertical rate and the ground speed. With some operations, with rotation matrices, we compute an apparent heading, apparent pitch, and apparent roll. We have plotted them here for one aircraft measurement. Thankfully, we also have the mod S messages. The mod S messages contain heading data and roll data, so we can replace the track data and the 0 we put in the roll and have more accurate measurements. And as you can see, in orange, I have now plotted the updated apparent aspect angles, and you can see that very clearly that while apparent pitch and apparent heading were quite good, apparent roll is really different when you take into account the mod S data. So obviously, I'm thanking Professor Sun for PyMod S. So a little video to show you in real time how the measurement pans out. We have a visual model of the aircraft, so you see the aspect angle in real time. We have the apparent angles being displayed, and we have the Doppler range maps, and you see that this red box is the window of interest according to the ADS-B data. This is what the window contains. This is the uncalibrated RCS. And as you can see, the ADS-B data allows for following the data. You can see that the data are not in the center of the window when the aircraft turns, because the speed data from the ADS-B data is not very accurate during aircraft turns, but I think you're aware of this. So, what are the conclusions? We have a database which uses both OpenSky databases, so the modest messages, the ADS-B data database, and the aircraft database. We have data from the OpenSky Live API, so the aircraft data and some monitoring data, because we want to know how the measurement went. And obviously we have radar data, which is the most important thing in our radar database, and monitoring data from the radar. So how do we go about and use all those data? So what we want to output with our database is obviously labels. That's the most tedious thing to harvest in any database. So we want the aircraft informations from the aircraft data we have stored. We want the aspect angles computed first from the ADS-B data and then refined with the modest data. And finally, we want the aircraft signature from the radar data and the ADS-B data. And the monitoring data we have gathered is used to make a quality assessment of what the aircraft signature data are. Finally, some limitation and foreseeable upgrades for our database. Sadly, we do not have any pitch data, but yeah, if airline want to provide that, we would be happy. Even historical data is not very accurate during aircraft turns. Our positioning algorithm for the turret uses a linear extrapolation, which is not very good. We should move to a Kalman filter. And we were using the Live API to track the aircraft in real time. It has a 0.2 Hertz sampling rate, which is not fast enough, so we will migrate on the Onera's ADS-B receiver, installed by Xavier Olive, to have a better sampling rate without stressing the API. And finally, the conclusion and perspectives. I think the method we have developed is quite adapted to different sensors, not only radar. We can do work on optical sensors, acoustic sensors. The generic selection rule we use to select the aircraft is, as we say, generic. So we could change it a little bit to gather different data. So for instance, we can augment diversity. So we want to select only aircraft we have not measured before. We can consolidate the database, so measure in priority aircrafts we have already measured. This method also allows for the testing of steering algorithms, such as the one we use to direct our turret to the aircraft, or that's for mechanical steering algorithms, but it can also work for phased array radar steering. And we are not only able to measure RCS, as I said, the radar we are using is a lot more capable than what we are presenting in this presentation. We could make high bandwidth measurements, for instance, for imaging or polarimetric measurements. So thank you for your attention, and if you have any questions.